All right. Okay, cool. So last time we started working through like our process of null hypothesis testing, okay, and talked through a number of different steps, right? We talked about first what we want to do is we want to state the null and alternative hypotheses. The null hypothesis is always nothing happens, sort of everything it goes as expected. There is no effect. Almost always our formal hypothesis is that some coefficient is equal to zero, okay? It doesn't have to be, it generally is, right? But remembering that we're only testing the null hypothesis with this procedure. The null hypothesis is the only specific hypothesis being tested essentially all the time. Anytime we're doing null hypotheses, or 99% of the time we're doing null hypotheses, the test is that my working model, or what my working hypothesis is that there's nothing to see here. That this coefficient equals zero, these two the differences between these two population parameters is equal to zero, that something is equal to zero. Okay, and that's the only thing we're testing. We have an alternative hypothesis, but that's oftentimes not super informative anyway, because we got a two-tailed test and we're saying like, well, it's just not zero, right? Or there is some difference. We have some evidence of a difference there. Okay, so we go through, we state our hypotheses, we set our decision criterion. The field generally sets our criterion. This is set at our alpha level, right? On our distribution, we're saying, okay, here's our markers, here's our goalposts, anything that extends beyond this, right? And so what the key thing to remember, so to make sure that you understand this, is that with our null hypothesis test, we're saying that assuming sort of like here's the expected distribution, assuming that the null hypothesis is true, right? So what we're getting with this whole process is that assuming the null hypothesis is true, assuming that the population coefficient is zero, assuming that there's no difference across these two populations, this is what the distribution of test statistics that we can see, right? But if we start to go through what we then do is create some goalposts, right? And we set those goalposts, and if our test statistic falls out in that critical region, right? What we're doing is we're saying, assuming that the null hypothesis is true, this is what we should see. What we're actually seeing in our observed data is something that's falling out there on the tails, which is then going to go through and influence the decision to say, well, we're going to reject the null hypothesis. We're saying that assuming the null hypothesis is true, this is what you would see. This is what we're actually seeing. That seems pretty extreme. And so as a consequence, what we're going to do is reject the null hypothesis, right? And this is where our p-values come into play. I told you in the example there was a sort of a literal interpretation of the p-value. You don't need to worry about that too much, but it would be kind of good to know kind of particularly specifically what that means. What we're getting with that p-value is it's telling us that assuming that the null hypothesis is true, there is a X% likelihood or X% probability of obtaining data these extreme or more extreme, right? And so it is giving us a probability statement based on this distribution. But again, assuming that the null hypothesis is true, right? Assuming that the population parameter is equal to zero, it would be very unlikely for us to achieve the data that we've seen, okay? So we go through and set these. This is generally alpha 0.05. This is we're generally working with two-tailed tests. So what do we have here, Abby, in this end of the distribution? Yeah, what proportion? Yeah, 2.5%, 2.5% here is where we go through and spread these out. We can do one-tailed tests, but we won't worry about those too much for this class, just for a lot of reasons. We got other stuff to get into, right? So we then go through, calculate our test statistic, and we go through and see where that test statistic falls on the distribution. In this case, right, we would say, assuming that the null hypothesis is true, this is where we should see most of our test statistics fall, right? If the population really is, in this situation, what are we looking at? Oops. Oh, antioxidant supplements, right? If the true population score for older adults taking antioxidants is actually 80, that we should get should be in here, right? In this first example, new clicker, I'm all over the place here. All right, we're right here. And so Olivia, what does this suggest about sort of our situation here? Right, where we would expect it to. And sort of as a consequence, what is our decision going to be with this? Okay, not quite, but I like that you said that sort of that the antioxidant an effect. That's our alternative hypothesis, right? So what's our null hypothesis? Yeah, that they're essentially that the mean memory score for older adults taking antioxidant supplements is equal to 80, which is the same score as the general population. Implicitly, we're saying that that implies that there's no effect, right? But that's the only thing that we're testing here. And so these data are specifically saying that if the mean mean score, cognitive score in the population actually is 80, i.e. equal to everybody else, these data would be very unlikely, right? Here we're saying there is a 0.3% chance of obtaining these data or data more extreme, assuming that the population score among older adults using antioxidants is actually equal to 80, right? So assuming that the null hypothesis is true, are the data that we've observed very likely or unlikely? Unlikely, yeah, because we're way out here on the end, right? People sort of get that in terms because that's going to be critical to some of the stuff that we're going to talk about. Yeah. Mm-hmm. Well, and we're going to get into some of that stuff because again, what you're saying, what sort of that your conclusion is what the vast majority of people will sort of say, just sort of casually as we're going through and looking at it, right? But again, our system is a series of indirect steps to go through and infer something that sort of may or may not be reasonable, right? So we're never testing the hypothesis that antioxidants have an effect. All we're testing is the null hypothesis is that antioxidants don't have an effect. Now, what we're saying is assuming that antioxidants don't have an effect. If we were to have a sample of this size and observe these data, that would be pretty unusual. Like if the true population parameter is equal to 80, for us to get a sample of whatever our sample was and to get a mean to, that would be pretty unlikely, right? And so what we would then do is reject the null hypothesis and we would say compatible with the null hypothesis mean cognitive scores in older adults using antioxidants is equal to 80, right? Now, what we get out of that is then saying, well, if these data were unlikely, assuming a mean population value of 80, then that I'm going to take that as evidence that maybe antioxidants do have an effect. But that's only indirectly we get there through rejecting the null hypothesis and saying, assuming that the null hypothesis is true, these data, it would be very unlikely to observe these data. If sort of our model is correct and all of our ancillary assumptions are correct, but we already know that all those ancillary assumptions are almost never correct, right? And so it starts to break things down a little bit, and we'll talk about that a little bit more about where the breakdown is and the consequences for interpretation. Yeah, Jalen. Yeah. Okay. So here that's a great question. Let's walk through this. Okay. What's the null value based on this model? 80. Okay. And can you tell me Jalen, how do we interpret that confidence bound? Or if someone wants to, almost there, fell off at the end. Range of scores is compatible with what? It's all right. It's all right. It's not about me, right? So, no, because I don't even say it because you're off. You're out. You're not. Yeah. Thinking too hard about it. Yeah. Yeah. Right. And if we're sort of getting sort of super focused on that precision estimate, that is, it's a frequentist approach, right? And so the idea is if we were to run this study an infinite number of times, right? And were to calculate confidence bands from each one of those infinite number of replications, this 95% would say that 95% of those replications would capture the actual population value. Okay. Do we know if this interval capture the pop? No, we don't, right? And so this is where sort of based on sort of the Cumming and Fitch article and things like that, I don't like the 90 getting too caught up with that, like takes us off in a weird direction, right? Because if I say there's a 95% chance that it ends in there, that says 95% of the time the population value falls between 84 and 100, and then 5% of the time it doesn't, right? That suggests that the population value jumps around. The population doesn't jump around. Population value is either in there or not, right? So the precision estimate is it's a statement about the process, right? If we were to do this over and over and over and over and over and over again, 95% of the intervals that we could calculate or would calculate would cover the population, would capture the population parameter. But the tricky thing is I don't have an infinite number of replications. I just have this study. And I don't know if this study captures it or not, right? So what I can say is based on the data that I've collected, data supported values for the population parameter fall somewhere between 84.2 and 99.8. Because all I can talk about is the data that I have. So I can say based on the data I have, supported values running from this to this, values outside of those, guesses for the population parameter that fall outside of those, could be, I don't know, but it's not consistent with the data that I've collected. And I'm assuming that my best guess is based on the data that I've collected, and the guess about things that are not the data that I've collected don't really make sense because I don't know, like lots of things. I don't know what if, like you can what if things to death. These are the data that I have. These are the values that support these are values that within this range contain values that are supported by the data that I have, or would be values that would be plausible given the data that we've had. Values falling in these are compatible with the data. Those values falling outside are compatible or would be non-compatible with the data. But see, as I'm going through and talking about these using these different this different language, it's all about things that are, would be compatible with the data or plausible given the data, or data supported values, or things that are consistent, right? Never with any of those things is it implied that this is a for sure thing, because none of it's a for sure thing, right? So Jalen, going back to your question, so the population value under the null is 80, right? Is 80 a plausible value based on the interval that we have? No, it's not, right? And so in this situation, are we going to reject the null or fail to reject the null? We're going to reject the null because 80, like sort of the test hypothesis, the test value is not reasonable based on the data that I've selected, which suggests it's a non-supported value. Does it mean it couldn't be 80? No, it doesn't mean it couldn't be, but from the data I've got, seems like that's not a reasonable guess for what we've got going on here. Okay. Now, if you could go, maybe, and this will happen, and it will happen to you, so you always have to make sure. We could go through and find that maybe instead of a mean of 92, maybe I get a mean of 74. Okay. Where's my test statistic going to fall then? Yeah, down on this other area, right? And now my upper limit might be of my confidence bound is going to be like 79 or something like that. What would I do under that situation? If my upper limit, if my upper bound is 79, the lower bound is like 60 something. If so, if my Z score is way down here. So if, let's say my confidence bound in this alternative scenario where we're seeing people actually perform quite a bit worse, right? Confidence bound runs from like 60 to 79. Where does 80 fall? Not in there too, right? So now we're just on the other side, right? And so thinking about like what would happen. So your question was, what would happen if my test value falls above this? That can certainly, it just means that we're performing worse than what we had expected, right? Which for this type of thing is important because I don't know, like sort of make people sort of super jazzed about you make all of these supplements, but I don't know, maybe it makes things worse, right? Exactly, right. Because then we would say, I mean, like, hopefully you would look at that and be like, Yikes, we need to go through and take a look at things." But yeah, with the one-tailed test, we're putting it all down here and saying nothing below this matters when things can go south on us sometimes, right? Does that help kind of understand? So the confidence bounds a little bit better. Okay. So really, the only thing that we're getting from our formal test here or our z-test is just this p-value, okay? And that p-value is literally giving us a probability statement that's saying, assuming that the null hypothesis is true, assuming that the population value is 80, a score of 80, then the probability of me obtaining data with the characteristics that I'm observed or more extreme is about 0.3%, right? I can go through and actually apply a very specific probability value that, but this is all predicated on assuming that the null hypothesis is true, right? Yeah. Yeah, that's kind of like you don't have to worry too much about the probability. I want you to know kind of what the probability, what the p-value actually means, but you got enough things to kind of pack into your interpretations. It starts to get a little bit bulky. But yes, this idea of data being compatible or consistent with or plausible and things along these lines, um, in my mind and in the mind of the American Statistical Society, tends to be a better way to be thinking about things, as opposed to this significant, not significant dichotomy, which we'll get into today. Yeah, yeah. Mhm. And we'll go in through. And so in this, what we're doing right now is we're using a very sort of rudimentary scenario where we know population parameters. We almost never know population parameters, and that's when we get into our t-tests. And so we'll jump into that once we finish up with this. Okay. All right. How are people feeling in terms of Mesa? I've had all my attention over here. I feel like you're neglected on this side. You're on my blind side right here. I said, like, yeah, no, but people comfortable with this concept because it starts to become critical with the stuff that we're going to cover today. Uh huh. Okay, which value? Because this is a critical mistake that people make every year. So people will say, in terms of trying to build an interpretation, they would say, well, I know that sort of I reject the null hypotheses based on sort of p-value or something like that, but so I look at my confidence bound provides additional evidence for the decision to reject because it doesn't contain the null value. Is that accurate? No, why not, Olivia? Okay, yeah. Could I ever have a like Could I ever have a p-value of greater than 0.05 and then have a confidence bound that that doesn't capture the null thing? Could I get discordance across those two? Yeah, why not? Yep. It's all the same damn numbers we're using to calculate all this stuff. Like there's no situation where I would get like a confidence bound that didn't contain the null parameter and a p-value that was like p equals 0.10 something. It's the same stuff. It's all the same information, right? So because I can't have a discrepancy between my p-value from my test and my confidence bound, it doesn't make sense that the confidence bound provides more information. It provides the same information. I mean, it does provide more information because there's more stuff to glean from it than just the p-value, but those two things can never be sort of different, right? So we wouldn't say like, oh yeah, like this is additional evidence for my thing because I used the same ingredients to cook one as I did the other. So it's all part and parcel the same, right? But getting to your issue here, Mandy, what people will sometimes do is make the mistake to say, well, my point estimate falls within my confidence bound. And so then that tells me I'm sort of on the right track. What's the problem with that statement? Your point estimate fall outside of the confidence bound? No, that can't happen either, right? This is always going to be, at least for the symmetrical confidence bounds that we're calculating for means and things like that, is going to be dead center, right? If your confidence bounds doesn't fall, or if your point estimate doesn't fall in your confidence bound, yeah, there's something that's gone wrong, right? But so you want to be careful, and when you're writing this up, right, to make sure that you're specific about when you're talking about the value, you need to tell me what value, right? The null value. In this case, the null value of sort of the under the null, a population mean of 80 is not consistent with the data. It's not plausible data with the data. It's not supported by the data that we've observed, right? It's not saying, I'm not saying that it couldn't be that. I'm just saying the data that I've got doesn't support that as a reasonable value within the rules that I've set up here. Yep, we know sort of by definition. Like, so this is just like if someone's just super into p-values and they want to see that p-value, that's what we're doing with the test. And we'll talk about that p-value does have some interpretive value for some things. But really, so the argument for the confidence bound is that's giving us, based on the data that we have, this is the lower bound estimate for whatever parameter we're trying to find, or the data supported low bound. This is the data supported upper bound. And so then sort of trying to infer things from that. All right. So, and then we talked about second scenario here, less of a mean value, less of a difference. Here, this is falling within the body of the distribution of scores that we would expect. And we would say, is the population value 80? Like, no, my guess is the population value is 84. But given sort of just what I would assume in terms of sampling error and things along those lines, this still kind of falls within the boundaries of it wouldn't be unexpected, right? So here my lower bound, my data support lower bound for my data supported estimate of the population value, 76.2, upper bound of 91.8. So this could be anywhere from something that sort of very much is consistent with that population value of 80, or maybe even a little bit less, to something that could be sort of way higher, right? Which is why when we get into sort of our interpretations, we're never saying that we've proven the null or that we accept the null, anything along those lines. Our null, if we turn up null results, it's ambiguous, right? We can't say it's inconclusive. Data are inconclusive. I'm not saying that the null is true. I'm not saying the alternative is true. I'm not saying there's an effect or it's not. I'm just saying from these data, we're not able to tell, right? It's inconclusive based on this, right? And part of that goes into things like power. So we had what, like 20 people in this sample or something like that. If I got 10,000 people in this sample, that p-value would be infinitely small, right? But my confidence bounds will shrink way in there, right? So for this, I'm not saying that supplements couldn't be helpful. I'm just saying that my data don't say that there's not much of my data to support sort of give me strong indication that they are, right? So again, thinking about sort of null results as just being inconclusive. We can't say one way or the other. We for sure aren't saying that the population, this mean cognitive score in the population of older adults using supplements is 80. In fact, our best guess says it's 84. But based on the data, we don't have enough evidence to say that it's not 80. If you ask me if could it be 80, I'm like, well, sure, right? It's not my best guess, but it's certainly within bounds. It wouldn't be incompatible with the data that I've collected, right? Yeah, under the null, yeah, because that always has to fall in that. What I'm interested in is the mean value under the null. Okay. All right. Yeah. Yeah. Nope. So what's the value under the null? What's my null value? No. So think well, in this case, I mean, it's do you remember it, right? So it's actional thing. So so what's on my number? 80, right? Remember, because what? Yeah, 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 yeah. So we know and so this is why it's always important to sort of, I want you to spend some time making a sort of both in statistical notation and sort of like talking about like the null hypothesis very clearly what that is, because our whole process is saying, is my data compatible with the null? Assuming that the null hypothesis is true, are these data compatible with the null, right? And in this case, we would say, yeah, they are. Is the null my best guess? No, my best guess is 84. But anything sort of based on the rules that I've set up before I ran the test, anything from 76.2 to 91.8 would be data supported values, reasonable guesses based on the data that I've collected. And so here I'm saying I would fail to reject the null and say that the best I could do was say that the potential effect of herbal supplements on or antioxidant supplements on cognitive functioning in older adults is inconclusive. We can't really say sort of one way or the other. It's a big this emoji, which feels real sad given sort of all the stuff that we've done, but that's essentially what it's doing. It's for sure not saying that we accept the null or that there is no difference or anything along those lines. Those types of interpretations will get you flagged on stuff. Yeah, Kate. Yeah. Yeah, that's brilliant, right? And why probably, right? I mean, on the reject, fail to reject, would it make a difference? No, but that's on a yes, no decision. What might my concern be if the lower bound on that was like 80.1? So the p-value is still going to sort of get what I want in terms of that reject, fail to reject, right? So I'm saying that antioxidants are helpful for older adults, right? But anybody who's taking supplements, sometimes it's not without cost. Sometimes you get GI stuff and it costs you money, and sort of sometimes it can go backwards and things like that, right? So if I'm saying population of older adults has a mean cognitive functioning of 80, and what's the lower bound in your scenario for what the actual population value for people taking supplements is? 80.1, right? So maybe it's not exactly the same, but my data are not super clear that it's making a meaningful impact, right? And so what I would probably do is sort of start to include some caveats in terms of practical implications for this. Be like, I don't know, sort of based on the data that we have, it could be anything from super big to sort of functionally identical as the same. So we have our data would support that there maybe is some difference, but again, because we have a difference doesn't mean it's meaningful, right? And so I would absolutely love to see you start to sort of pull some of that stuff in, right? Thinking about what are the implications of this full range of this confidence bound. Right. Yeah, Abby. No. Yeah. Mm-hmm. Yeah. Yeah. So you're absolutely right, but look through and make sure that you know why that's the case, as opposed to just trying to memorize that as a thing, because that'll take you sideways. Yeah. Okay. All right. So we went through, talked about one-tailed, two-tailed, and then we're going to draw our conclusion, right? Based on how we approach this, we have a dichotomous decision. We either reject the null hypotheses or we fail to reject. Reject is when we're seeing our test statistics fall out on the fringe, that we don't make a specific assumption or interpretation about the alternative. All that we're saying is that these data, the sample data, are unlikely, assuming that the null hypothesis and all corresponding assumptions of the statistical model are true, right? So assuming that we haven't violated any assumptions and the true population value is 80, these data are very unlikely, right? And then the leap that we likely a population mean that's different than what was specified under the null, which is taken as indirect support for alternative, but we're never directly testing the alternative, only the null. Okay. And if we fail to reject, this is when we got a test statistic in the body of the distribution. This is where we're saying sort of generally it looks like the sample data that we've got are not incompatible with the null hypotheses. The null hypotheses is reasonable given what we've observed, and as a consequence, we would fail to reject the null. That's not saying that there isn't, that the null hypothesis is true, or that there is an effect, or that we should never ever do this again because my study has basically ruled out the possibility of anything ever happening. We're just saying based on the data that we've collected, we can't say one way or the other whether or not we have evidence for an effect. Okay. All right, so people kind of sort of getting a good sort of at least feeling solid on sort of this reject, fail to reject decision and what the implications are. Okay. All right. So we've gone through and sort of given some examples of sort of how we might go through and interpret these. So go through and take a look at these. Again, do not copy and paste these. These are my interpretations, not yours. I just want you to give you an idea of how we might start to try and knit this different pieces and components together. And as you're going through and working through your sets, I would strongly encourage you to go through and play around with kind of the structure and how you're going through and pulling things together. This is just going to make you more flexible. The time efficient trap that people will sometimes do is like, I just have my stock paste in phrase, and then I'm just going to drop in, sort of change the statistics around. The problem is that you're going to miss some statistics, and that interpretation might not make the most sense depending on sort of the questions that you've got. And then 3, you're just not learning how to sort of go through and integrate this sort of well. So change this up. But again, here going through and trying to talk about what you were talking about, Kate, here is we're saying, you know, even for the in the scenario where we do reject the null hypotheses, I would say it's important to note that estimates supported by these data are compatible with meaningful elevations in functioning relative to the general population, as well as low Brown estimates that fail to exceed the threshold of practical effects, right? And so while these data do give us reasonable support for the possibility that antioxidant supplements do have a positive impact on memory performance, we're still not, based on the data, we still can't say definitively whether or not that's a meaningful impact, given that we're saying change sort of a difference greater than 10 is going to be sort of what we're looking for. My point estimate is promising, right? My point estimate is 94. That's an increase of 14 points. So my best guess in this interval is still consistent with positive and practical effects, but I don't have many people in my sample. My confidence bound is pretty wide, right? And so the low bound on this 84.2 would suggest something that is better than 80, but maybe not in a practical sense, right? And so we have to keep in mind that probably what we would want to do is have maybe more controlled designs, samples or studies with more people to try and get a more precise estimate. Because right now we've got a signal, we just can't make super strong statements about the extent to which this is important or sort of could be impactful for our clients. Yeah, Johnny. Yeah. Yeah, no, that's an error. It's well, So, and this is, no, it's not an error. This is me fooling around with stuff. If you go through, if I'm taking so the P is a two-tailed test. So do you have your Z table? Does someone have a Z table? You got it. Oh, yeah. What is for a Z score of 3, what tail? No, the smaller. Yeah. And that's where this is coming from. So I was just sort of in this being technically correct, because if I'm just looking at a straight probability value with a Z score of 3, the probability of me obtaining data, assuming that the null hypothesis is true, the probability of me obtaining sample data with a mean of 92 or higher is essentially 0.1%, right? Now, for our actual two-tailed test, what we have to do is we have to take that p-value that Olivia stated, multiply it by 2, which is what gets us to our 0.003. And so that changes the interpretation a little bit, I would say, to obtain data that are this extreme or greater would be sort of this, because we're taking into account possibility of it being sort of on the bottom end too. So, but again, want you to understand where these p-values are coming from, but I don't necessarily need you to sort of work that. And if you want to, that's cool. Don't feel like you have to. Okay. I'm already asking you to pack a bunch of other stuff in there too. So this piece, just that piece. You don't have to give me sort of specific database probabilities on sort of what's happening. Okay. But I do want you to kind of know where those are coming from. Okay. All right. Scenario 2, same thing. Okay. All right. So that took some time, but I think sort of worthwhile going through and making sure we're clear on what we're all talking about before we get into the next stuff. Okay. So last thing we want to talk about here before we get into sort of why this is problematic, want to talk about some different error types. Type 1 error, this is where I'm rejecting the null hypothesis when the null hypothesis is true. There is no difference. The population mean is 80. And what I go through is I go through and claim an effect when there is in fact no effect. This is my type 1 error. Okay. Historically, this has been associated with the selection of a chance selection of an extreme sample, right? And you'll see this in like undergrad textbooks and say the probability of randomly selecting a sample that is sort of beyond this is sort of whatever. In actual fact, in applied stuff, it's usually not because of no chance, because there's all sorts of other things that can go wrong to say, oh, this just happened there is no population difference. The population mean is 80, and I just randomly happened to catch someone with a group of X individuals with a mean value of 92, just happened by chance. Maybe, probably not. It's probably due to measurement issues. It's probably due to non-random sampling and things along those lines, right? But historically, what we've said is that, all right, here is the null value, right, is equal to 0. So there's some difference, right? And what I've done is I've gone through and accidentally grabbed something out here. Probability of doing this is say 0.02, right? Here's the actual sort of population value. It's rare for me to get a sample that falls out here, but it's not impossible, right? And so if we did that, and so the population parameter is here, we found something that's associated way out here, but it was like a 1 in 1,000 chance of me doing that, we would say that I've made a type 1 error. I've claimed evidence for an effect when there is in fact no effect here. Okay. Other type of error, sort of this is determined by our alpha, right? Again, alpha 0.05. This is basically saying a 1 in 20 chance that I'm going to accidentally, everything else has gone right, but I'm just gone through and sort of mistakenly grabbed something that's hanging out here on the end. Alpha 0.05, this is convention, sort of 1 in 20 chance, right? Assuming the null and all auxiliary hypotheses are true or haven't been violated, we got like a 5% chance of sort of falling in sort of one tail. If we go through and set alpha to 0.01, we're saying a 1 in 100 chance. Again, we're going to reject when the probability of obtaining the data, assuming the null and all auxiliary hypotheses is less than or equal to a 1%. Okay. This is just basically setting the boundaries for what we can claim as an effect in these data. Okay. Yeah. Talk about why that starts to become problematic, right? What this should do, Danielle, is start to be thinking about, I mean, we default to 0.05 because that's sort of what we always do, right? But there could be some situations if I'm, let's say, sort of working with maybe a really intensive, like say medication or something like that, where I can't get a lot of people. And what I'm doing is very expensive and labor intensive. And sort of the practicalities of me getting, 100 people that's not realistic. What I might do to avoid, a different type of errors, I might sort of want to say like, well, I'm going to change that down, not 0.05, I'm going to sort of move it down to 0.1 so I don't make a different type of error, right? If I've got something, if the possibility of me sort of missing something important is super consequential and has big practical impact, I might make an argument for moving this down a little bit, okay? But for the most part, our type 1 error in our field, we don't want anybody getting anything for free. We don't want anybody being able to claim something that's not there and being able to get all the credit and glory. And so what we're primarily focused on is our type 1 errors, right? Having a threshold for high threshold for claiming an effect, so that we're not claiming an effect when there is in fact no effect out there to be had. But that comes with costs that we'll talk about in a moment. Okay. So again, here's what we would do. Again, if we're using Z tables, Z scores, these are all the same. If I have alpha 0.05, my Z scores threshold 1.96, 2.58 for a 1, 3.29 for moving out, right? Is just kind of our standard set scores if we're using a Z distribution. Okay. Other type of error we have is our type 2 error. Okay. Our type 2 error, this is the error I make when I fail to reject the null hypothesis when the null hypothesis is actually false. So there is an effect out there in the universe. There is a relation. There is a difference. But what I do is I don't claim evidence for it. And so I fail to reject the null hypothesis when the null hypothesis is in fact false. Okay. This is generally associated in statistical analyses when I don't have sufficient power. Okay. Going back to our supplement example where we had a point estimate for older adults taking supplements was 84, right? Now with the sample size that we had, we failed to reject the null hypothesis because we had a pretty wide confidence bound, right? Our test statistic fell within the body of the distribution. And so we're saying that we don't have evidence for an effect. I'm not saying there isn't an effect. I'm just saying I don't have evidence for effect. But again, if I were to crank up the sample, right? Allison, if I were to get a sample of 500, what would happen to that confidence bound? It would shrink up, right? And so now if I'm catching 80 on the outside and all of a sudden that confidence bound shrinks up, now all of a sudden what happens? It won't fall in there, right? And so what ends up happening, I may still have the very same point estimate. I just have more power in that sample, right? Which is again why we don't say just because we turn up no results, we don't say that there is no effect. We're just saying we don't have evidence for. But if I get a lot more data, gives me a much more precise estimate, I may be able to say, yeah, there is an effect. It looks like we're seeing about a 4-point difference is our best guess due to supplement use. Now, whether or not that's a useful increase, that's a whole different situation, right? That starts to get into our effect size, but we at least have some evidence that the mean cognitive functioning score in older adults who are using supplements, it's not exactly 80. It's something different based on my well-powered study. It's 84, but if I don't have power, I don't have as much precision, my confidence bound is wider, I capture that null parameter, and so I would fail to reject, and I would have, in that case, made a type 2 error. Yeah, Mandy. Not a lot of observations, right? So not a lot of people in the sample. Yeah. Yeah. Yep. So if I were to go through, what I could find is if I were to redo, so let's say Allison redoes the supplement study with 500 individuals and she gets the same, very close to the same point estimate of about 84, right? But because she's got a lot more people, what's going to happen to her standard error? Yeah. And so what's the standard error going to do? So if our standard error, square root of our variance over our sample size, my sample size goes up, what my standard error? It goes down. And if my z-test is, so the mean, oops, x minus the mean over my standard error. As my standard error goes down, what happens to my z-score? Yeah. So we're dividing sort of this by a smaller number. Z-score goes up. My z-score goes up. What's the likelihood of me claiming evidence for an effect? Better chance, right? And so in this situation, the point estimate that I got in my first study with antioxidant supplements was perfect. I was dead on the money, right? But I couldn't claim evidence for an effect because I didn't have enough power. Allison redoes the study, which much more people, she still gets the same point estimate. It's just sort of a much more precise estimate that we can then rule out the null value of 80 as a possibility, right? And so this is the thing that's important to think about. Like, so these two studies basically gave us the exact same point estimate, but gave us very different conclusions on reject, fail to reject. The effect size is identical. The point estimate is different or identical. The only thing that's different is Allison had a whole lot more people than I did. Okay. But then this starts to sort of lead into this sort of concern about what we're actually doing with these tests. And sort of if statistical significance is just almost 100% purely a function of how many people I can shove into my sample, starts to question what this is actually doing for us and what we're actually learning. Okay. But what it does is it makes it much less likely that we're going to go through and find a type 2 error here. Okay. So type 2 error, greatest concern where I have a treatment or manipulation has a small but reliable effect. Okay. I have the effect that I'm looking for is not large, but that doesn't mean it's not important. It's just pretty subtle. This is what happens in almost all of the effects that we're looking at in social sciences. But what we've got is because of sample size, poor measurement, sort of these types of things can all start to lead to these type 2 errors where there's an effect out there for me to find. I just haven't found it. Okay. So this little matrix, I'm sure you've all seen it before, a sort of a nice way to go through and think about things. No effect, effect exists, reject, fail to reject. If there's no effect and the null hypothesis is actually true, and I reject the null, or excuse me, and well, let's start over here. An effect exists and I fail to, or excuse me, and I reject the null hypothesis, then I've made a correct choice. If there's no effect and I fail to reject, then I've made a correct choice. But here's my type 1 error, my type 2 error. Here, I'm saying that there's something when there is in fact not. Here, I'm saying we don't have enough evidence to claim an effect when effect does exist. So these are the balances that we're making here. And this will get into our discussion of power and things along those lines when we get there in a few weeks. Yeah, Daniela. Yep. 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 We never ever in this situation, we're saying out like the objective reality is that there is no, right? We can never know that specifically, but we're saying hypothetically, if in fact supplements have zero impact, right? And so you can take supplements all day long if you're an older adult and the average cognitive functioning is still going to be the exact same as it is for everybody else because this doesn't do anything. In the universe, there is no effect here, right? And so if we then we're to get a sample and conclude that there was an effect, when in fact there actually isn't one, we would have made our type 1 error, the type that we sort of start to get really worked up about. But what we do is, and we'll talk about from philosophical reasons, this is sort of probably the one that we make much more often, but we don't sort of get as worried about it because no one gets anything free if they fail to reject the null hypothesis. But from a science standpoint, we probably should be much more concerned about this. All right. Okay. So underpowered studies, these tend to be the most common things that go on, right? This is almost like we have huge power problems because we're almost always looking for small effects, and we almost never have enough people to adequately power our studies to detect the effects that we're chasing down, right? And so we often sort of have concerns about or this is the error that we're probably making, and so this is problematic. But there are certain times where overpowered studies can be problematic as well. Okay, so let's go back to a sort of Kate's example where the actual true population score for older adults taking supplements is, we'll call it 81. Okay, and what I do is I just get government data and I get 10,000 observations. So I'm working sort of thing where so it wasn't around because I told you I was working on a census project, right? So this is government data where got like 8 million observations or something like that, right? If I have that power, anything's going to be different, right? I could have like literally have a mean difference 80 versus 80.1, and that's going to come up with an infinitely small p-value, right? And so what I can do is I can start making inferences about sort of this thing, or let's say a correlation. If I have a correlation with that many observations, all my test is telling me is it exactly 0, right? And if my p-value is very small, it's just saying my data is just saying that it's not exactly 0. It might be a correlation of 0.01, but it's still going to come up as significant, right? And here we've got a problem with an overpower issue, right? Because then I just got so much goddamn data, everything comes up as significant across the board, and I start talking about significant effects right, left, and center, when in fact, all the effects I'm finding are super trivial and probably have no sort of practical meaning for anything, right? And so we'll get into sort of some of the traps that we can fall in sort of once we jump back after break. Yeah. Yeah. Sure. Yeah, no, and power analysis is always fantastic. Now, in our field, in our area, you're probably not going to get, there are probably not too many cases where you're going to get something that's overpowered. But even if you do get an overpowered study, if we're looking at effect sizes and thinking about practical implications, doesn't matter because we're less concerned about that yes, no decision, like do we have something, do we not? What I'm starting to think about is like, so what is this? Is this meaningful given the context I'm thinking about, right? And then the p-value doesn't matter. That's a more conceptual issue. Yeah. No, this is sort of, if I have too much power, anything comes up as significant. There's always differences. Nothing is exactly equal to 0. There's always some trivial difference between something, right? The relation between X and Y is never exactly 0. The difference in the population means is never exactly 0. And if I have if I have an overpowered study, everything's going to come up as significant all the time, right? And so if I'm not being careful and don't recognize that, what I can start doing is start claiming sort of big implications when in fact, sure, the association between X and Y isn't exactly 0, but it's 0.08. And I don't know who gets super jazzed about a correlation of 0.08 outside of some very specific situations, right? And so I can start making claims and inferences that aren't probably supported by the data if I'm just sort of basing things on yes, no, sort of a significant, not a significant. Well, they use different models with different standard errors and different assumptions, and a lot of times you have 5,000 sort of predictor variables in there that's like literally sucking out any possible other things that are going on. So there's different stuff that goes on in that. So yeah. Okay. All right. Is this a reasonable procedure? Let's go through and have a break, and we'll go through. I think this was good. It was a lot of review to get through a couple of different slides, but I think this will set up the discussion for why we need to be very careful about how we're interpreting our tests. So let's go on break. We'll jump back. Yeah, let's try and be back. Take a short break. Try and be back by 3:40, so that we can jump through and get into this stuff here. All right, folks. So let's jump in and start talking about sort of the criticism. Yeah, I did. Yeah. Thank you. Yeah, I did. Yeah, no, it says it should. Okay. So we've talked about sort of the basics of null hypothesis testing. We're using this a very sort of simplistic z-test types of things, but the idea and the process and sort of the logic behind it is the same for z-tests versus SEMs and sort of multi-level models and sort of all of this, right? And so it's a pretty slick system, we've sort of used this system since before the early 20th century, right? In terms of sort of putting all this stuff together. But this has been widely criticized since the beginning. And from the field of psychology, so we start going back into the 60s, and people have criticized this in very, very colorful ways, right? In referring to null hypothesis testing, this naked emperor has been shamelessly running around a long time. I argue that null hypothesis testing has not only failed to support the advance of psychology as science, but seriously impeded it, right? Wide agreement among many statisticians who have studied the issue for reporting statistical tests yielding p-values. It's illogical and inappropriate to dichotomize the p-scale and describe its results as significant or non-significant. Authors are strongly discouraged from continuing this never justified practice that originated from confusions early in the history of modern statistics, right? So in Wasserstein here, we conclude that it's time to stop using the term statistically significant entirely, nor should variants such as statistically different, non-significant survive, whether expressed in words, asterisks, or in a table, or in some other way. Like, so these are some of our most revered methodologists and folks from sort of modern statistical analysis saying the way we do this is problematic for a lot of different reasons. Okay. And this isn't new. This isn't something that has just come up. This has been going on for a long time. Okay. And sort of we've known this for a long time. We continue to sort of misuse and misinterpret our statistical models. But the problem is if we go through thinking about a couple of different reasons, right? We've got some methodological reasons, some conceptual reasons. So the philosophy is a little bit backwards. Sort of the methods we use is a little bit backwards. The meaning we attach to it is a little bit backwards, right? Again, this isn't to say that it's without use. It's just like any tool, if we don't use it correctly, we can get ourselves into trouble, okay? So first thing that we run into, criticisms about the fundamental logic of null hypothesis testing, okay? The scientific question that we have, that all of us sort of are interested in asking when we go through and gather data, right? We gather data and we want to say, given the data that we have, what's the probability that the null hypothesis is true, okay? So I want to know if there's a difference between group A and group B, right? And so, or Jalen does. And Jalen goes out and gets a bunch of data from group A and group B and wants to use those data to try and say, what's the probability that the null hypothesis is true, that there's no difference between these groups, right? that seems like a reasonable thing to ask. What we actually get with our null hypothesis test is a little bit different. Null hypothesis test, the actual procedures that we use, ask a different question. Given that the null hypothesis is true, what is the probability of these data? Okay, this is what we went through, and we spent all this time sort of on the first half. Again, assuming the null hypothesis is true, this is the distribution of statistics I should get. I've got something that's not consistent with, I've got data that sort of fall outside of that, and so I'm going to make an inference about the likelihood of the null hypothesis, right? What I want to ask is, given the data, how likely is it that sort of there is no difference? What we're actually doing is assuming that there is no difference, what's the likelihood of the data, okay? And what happens is we get down in a break. Who's had philosophy classes or sort of done some philosophy stuff? Did people get sort of far in philosophy more than just like intro philosophy? Okay, a little bit, right? And so part of sort of what we're doing in philosophy is like thinking about arguments, right? And so if we were to say, if the statement was, if the null hypothesis is true, these data cannot occur, right? If we have a definitive, clear statement like that, then we could say, well, the data have occurred, therefore the null hypothesis is false, right? And if that's what we were doing, then there's stuff to be learned from that. But what we do is we change it a little bit, right? Is we say if the null hypothesis is true, these data were unlikely to occur. That's what we've been talking about all afternoon, right? If the null hypothesis is true, these data are unlikely. These data have occurred, therefore the null hypothesis is unlikely to be true. This is the logic of null hypothesis, right? The problem is, as soon as we start substituting sort of other examples in with this sort of basic logic chain, it starts to break down pretty fast, right? So again, if we take this, if a person is an American, he or she is unlikely to be a member of Congress. That's a true statement. Person is a member of Congress, therefore they're unlikely to be an American, right? You're just substituting different things, and now all of a sudden you can start to see that the logic has problems and is not sort of consistent, right? Now, if we go through and we say if a person is an American, he or she cannot be a member of Congress. Now that wouldn't be true, but like this person is a member of Congress, therefore this person cannot be American. Sort of based on the statement that we've got, that would make sort of consistent sense. But as soon as we go from cannot into likelihoods, now all of a sudden things start to get screwed up. Okay, so we've got problems with the fundamental logic. Like this, if we were saying if the null is true, these data can't happen, we would be okay, but we don't. We tweak it just a little bit to try and infer something about the likelihood of the null hypotheses based on the likelihood of the data, and then start making conclusions that can very quickly start to be shown to be nonsensical with stuff. Okay, so the fundamental thing here is that the question that we're wanting to ask is not the question that we're asking with null hypothesis testing. And just the logic with this starts to break down pretty quickly. Okay. In that Cohen paper I have you read, talk about this as the illusion of attaining improbability, right? It seems like the null hypothesis shouldn't be true because these data are unlikely, but that's not actually the scientific question that we're asking. What we want to know is, given the data, what's the likelihood of the null? What we get instead with our procedure is, assuming that the null is true, what's the likelihood of the data? And we can start to get very different answers based on those two things. Okay. Part of this comes from the fact that these are non-equivalent probabilities. Okay. Again, the scientific question is, what's the probability that the null is true given the data? So here in notation, we have the probability of the null given the data. That sort of upward slashes sort of say given, right? So the probability of the null given the data, but what we're getting with our statistics test, our inference test, is the probability of the data given the null, right? And so if we, again, use some just basic concepts from philosophy and logic arguments, we can quickly start to see how these two things aren't interchangeable with one another, okay? The probability you speak English if you attend this class versus the probability that you attend this class if you speak English, right? We flip those two things around and we've got very, very, very different probability statements, right? It looks like this should be a trivial difference, and it's in fact not. It's a very, very substantial thing. And so with very, very little like philosophy 1000 approach, you can start to break down the underlying logic of our null hypothesis testing, okay? So what we're doing is we want to reject the null in an effort to conclude that the null hypothesis is unlikely, right? We can see where this falls apart in sort of from a logic-based standpoint. But if we start to go through and start to work with the math, we also see that this falls apart real fast because this just isn't how the math works on this. In order to calculate the likelihood, the probability that the null is true or not, we would call that a posterior probability. This is a probability statement that or a probability estimate that we've generated after we've gone through, collected the data. But in order to do this, what we really need, and this is where we get in some Bayesian approaches, is what we need to know. We need to know the probability of the null hypotheses before we conduct the experiment. We call this prior probability or priors in Bayesian stuff. Problem is we can't calculate that accurately because we don't know the probability of the null hypothesis before we go through and start collecting data on stuff. Okay. Now Cohen gives an example. This is the same example given in Cohen, but I think it's just really illustrative. We can start to walk through how we start to get into problems with this. Okay, so let's take something that we do know prior probabilities on. Okay, we'll say schizophrenia. Okay, we know that base rates of schizophrenia in the population are about 2%. Okay, so if I were just, at least in the US, so we go through and I say, get everybody in the US, base rates of schizophrenia diagnoses, about 2% of the population, right? So we would say here, prior probability, the probability of schizophrenia is 2%. Okay. And we know this before running any types of tests. This is just something that we're aware of, right? So we have a prior on this. Okay. And what I've done, we'll say, again, Mesa, you're in my blind spot. This gets to be your test. Okay. Mesa's put together a test that's looking at a test for schizophrenia. Okay. And you've got this measure that is demonstrating 95% accuracy for a positive diagnosis and 97% accuracy for negative diagnoses. Mesa, are you happy with your test based on those statistics? Yeah, I would be. I'd be super jazzed about that. That's incredible, right? That seems like we're doing pretty good stuff here, right? And so if we break this down into notation, right? Our null hypothesis is that the case is normal. There's nothing going on. Our alternative hypothesis is that the case has a diagnosis, okay? And then T is just going to be our positive or negative test, okay? So if we go through and we look at the probability of a positive test given an actual diagnosis is 95%. This is that sensitivity piece of things. Oops. Right? So this is saying of those with the diagnosis, what's the proportion that are going to be detected by my test? 95%. That's pretty good, right? Here I've got the probability of a negative test given a normal case is 97, right? 0.97. This is telling me of those without a diagnosis, what's the proportion that are going to be correctly identified by the test? 97%, right? We're all pretty jazzed about this. Mesa, if you choose to copyright your screening, you will likely make quite a bit of money off of this. Okay, so we're feeling pretty good, right? We're feeling really good about the accuracy of this test. Okay. So if I want to take a look at the probability of a positive test given a normal case, I can calculate this as 0.05, right? And this is basically our alpha, right? This is our type 1 error, right? We're saying, given the data, what's the likelihood of the null positive test? What's the likelihood of a miss? If we take this minus or 1 minus this, it gives us 0.05. This is basically the same scenario that we're setting up in our hypothesis test, a test that sort of in a criteria that we would say is acceptable, right? Based on how we set things up, okay? In this case, we would conclude that this is an unlikely outcome. And what we would do is if the test is positive, we would say that the person is positive, is a positive for schizophrenia because I've got a pretty good test that's pretty good at accurately assessing things, okay? Now, this, though, we start to get into sort of that scientific question of interest, right? The probability of a diagnosis given a normal case is not the same thing as the probability of a normal case given a diagnosis, right? We can't switch those things. Or the probability of the data of a positive case given the null seems pretty unlikely, right? But this isn't the question that we really want to ask. We want to say, given a normal case, what's the likelihood of getting a positive diagnosis? If I'm just looking at this, it seems like that's pretty unlikely, right? Because this is so, but again, we've got probabilities that aren't interchangeable. If I want to do this, and this starts to become important too, like I've got someone who comes in who does not have schizophrenia. What's the probability of me getting a positive test, given that I don't have schizophrenia? If someone doesn't have schizophrenia, you shouldn't tell them that they have schizophrenia and diagnose them with schizophrenia. That's pretty intense, right? In order to do this, what we need to do, if I do really want to know the probability of a normal case given a positive test, right? What's the likelihood of the null hypothesis given the data, the scientific question that we want to ask, the calculation starts to become a lot more complicated, right? I have to know the probability of the null, right? This is my prior, and multiply that by the probability of a positive test given a null normal case over the probability of the null times the probability of a positive test given a normal case plus the probability of diagnosis, or the base rate of diagnosis, plus the multiplied by the probability of a positive test given a positive case. And what we can do with this is, because we have all this information, we can actually start to plug that in, right? So here, the probability of a non-case is going to be 98%. We know the base rate of schizophrenia is 2%. So we know that 98% of the countries doesn't have schizophrenia. Multiply that by the probability of a positive test given a null case, that's 1 minus this, right? It's what's left over. Down here, the probability again of no diagnosis times the probability of a positive test given no diagnosis, plus the probability of diagnosis, plus the probability of a positive test given a positive case. If I actually work that out, I find that the probability of a normal case having a positive test is about 61%. What this is saying is it's saying that 61% of the people who come up with a positive test are not going to have schizophrenia. Yeah. 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 Let's see that. Look at that. And this is why I don't want to ever want to hear anybody back. Oh, when am I ever going to use this? I don't know. You didn't know that you were going to need that philosophy cast until right now. This point right now, right? Doesn't matter. You've already got it. And so we can go through and take a look at this very, like, let's say a small case, like we've got 1,000 people, right? And so if we go through and we kind of set this up, if we go through, someone have a calculator. Someone got a calculator? All right. Allison's got it. All right. So if we have we have people without a diagnosis of schizophrenia, right? And I take 949 and divide it by 979. Tell me what you get, Allison. .96, about 97 if you round it. Yeah, right. Okay, yeah. So what this is saying, of those without a diagnosis, how many, what proportion were did we say had negative? Looks pretty good. 97% of the normal cases came up with those cases. Don't put it down yet. Yeah. Okay. Take 1 divided by 21 and tell me what you get. Or whoops, take 20. So it's 20 divided by 21. Okay, right. 0.95. So of the people with schizophrenia, our test got 95% of them, right? But if we start asking, of those who received positive tests, how many of those people were normal? Now all of a sudden, if I take 30 divided by 50, it's something pretty close to that, right? What this does is what we start looking at is, and again, for those of you taking assessment, this is an issue of positive predictive value. Sensitivity specificity says of our entire population, of the sort of total group who has sort of whatever it is, how many of these are we capturing by the test? Positive predictive power flips that around. It says of the number of people who are identified by the test, how many of those actually have sort of the thing that we're looking for? And here, our positive predictive power is pretty poor, right? It's going to actually be 20 divided by 50, right? And what this means is we've got a whole bunch of false positives, right? And depending on what we're testing for, that false positive might be incredibly consequential in terms of things, right? And so basically what we've done is if we go through and we take a look at this, we say, yeah, boy, the probability of getting a positive test for someone who doesn't have the probability of a positive test given a normal case is quite low, right? That's what we're doing in our null hypothesis testing. And so we would say, yeah, the likelihood of making a miss and making an incorrect decision is quite low. But what we're actually wanting to know is the probability of a normal case given a positive test, right? What we actually want to know, the scientific question of interest, is the probability of the null hypotheses given the data. And if we do that, we see that that's actually associated with lots and lots and lots of misses, right? And so again, like if we go through both from a philosophical standpoint and a mathematical standpoint, basically this problem of the fact that our tools aren't answering the question that we actually really want answered is problematic. And if we pretend that they do answer the question that we're asking when in fact they don't, and try and ignore this piece of things, what we can do is we can start to make pretty problematic decisions about the state of things out there in nature. Okay. Now, what's the thing that's contributing? Now, this is a pretty extreme example, but I mean, it's a good example, but what's contributing to sort of this issue here? Really low base rate, right? If I'm sort of a criminal researcher and I want to develop a test for serial killers, what's a way for me to get a really, really accurate test for serial killers? Mathematically, at least. I can get super accurate right now. I'll just say that no one's a serial killer. And I'm going to be right 99.999% of the time, right? So mathematically, I've done a great job, right? But for the purpose that I'm trying to get at, I've done a very poor job because I've missed everybody sort of in there. But it's a low base rate issue, right? And so this starts to create some of the discrepancy. But if we think about this, well, what's the probability of the null hypothesis before I enter? I don't know. There's probably cases where the probability of the null hypothesis is very, very low already, right? And so the probability of the alternative is already really low, and so that starts to impact things. Okay, yeah. That's a methods question though, where we can start to go through and start sort of better manipulations, right? Stronger tests, better measures, and things along those lines, right? But just as a demonstration of that our tools aren't doing what we think they're doing, and that's a problem, or can be quite a problem, is something that methodologists have argued that we probably shouldn't be ignoring. Right. All right. Another philosophical criticism is we go through and test the null hypothesis. Our entire focus is on the null hypothesis, right? What's the likelihood of the null hypothesis, right? And we're very, very caught up in rejecting or failing to reject the null hypothesis. There's a very, very strong and consistent argument that the null hypothesis is always false to some degree, right? Probably, if we get sort of a precise enough measurement, the population means for two groups are never going to be the same. Their association between A and B is never going to be exactly zero, but that's what our test does. It says, is this thing exactly zero, right? And so Cohen, saying can only be true in the bowels of a computer run a Monte Carlo study. Even a stray electron can make it false. So if the null hypothesis is always false, what's the big deal about rejecting it, right? It's foolish to ask if are the effects of A and B different? They're always different, some decimal place, right? This is maybe my favorite here. Statistical significance testing can involve a tautological logic in which tired researchers, having collected data on hundreds of subjects, then conduct a statistical test to evaluate whether there were a lot of subjects which the researchers already know because they collected this data and they know that they are tired, right? If the only thing that drives statistical significance is the size of or not the only thing, but one of the major things that drives statistical significance is the number of people I have in my sample. You want your dissertation to work out wonderfully and have effects, you just get 1,000 people in your sample, stuff's going to come up, right? But the question is, at that point, do I really need? Do I want to put that much effort in to get statistical evidence to tell me that the relation between A and B isn't exactly zero, or that the difference between these two groups isn't exactly zero? I already know that I'm going to have evidence that it's not exactly zero because I collected a crap ton of data on a huge sample. And I know if I do that, then something's going to come up, right? And so if we start thinking about sort of the impacts of power and so the value that we put on rejecting the null hypothesis, well, you just get enough people and you're eventually going to reject something, right? Starts to call into question the utility of the whole endeavor, right? So again, from Cohen's perspective, we could say, regardless of the specified theory, rejection of the null hypotheses is expected in the predicted direction half of the time. Okay, if we take and we say that if the question is, are population means for A and B different, and we just accept the fact that they're always going to be different to some decimal place, they're never going to be exactly the same, right? With sufficient power, sort of when I'm going through and looking at this, and even if they're very close, right? Half the time I'm going to fall on this side, half the time I'm going to fall on the other side. So even if there was sort of really no meaningful difference, half the time my direction is going to go in the direction of my theory. The other half it's not, right? And so this idea that this test supports my theory is nonsensical, because even if there's sort of a near null effect, the other half is going to support the other sort of the direction against half the time anyway, right? Now, if I have a theory that starts to align with the actual differences that we see in the data, then I'm going to reject more than sort of 50% of the time, right? If I say, Mandy, again, remind me what your interests are. Okay, so you're saying that there's an association between first generation status and self-handicapping, okay? And you have likely a sort of theory sort of that goes sort of for that. But I have an alternative theory. I have a theory that first generation students are impacted by space rays from Venus that cause them to self-handicap more often than people who aren't first generation. Don't ask me why, but I'm very invested in this hypothesis. But I go through and I find data that consistently supports my predicted association between first gen status and handicapping. And I say, space rays from Venus. What did I tell you? I got data that support sort of my theory, right? I got a random ass theory that has nothing to do with actual real life, right? But what I'm doing is that my theory aligns up with sort of more plausible mechanisms for why those two things might be related. And even if there wasn't a relation there, and I go through, half the time I'm going to go, my point estimates are going to fall on one side, half the time my point estimates are going to fall on the other side. At the very least, half the time my space ray from Venus hypothesis is being supported by the data, given sufficient sample size, right? And so again, sort of starting to question this idea, if the null hypothesis is always false, like why do we sort of, there's always a difference. There's always a difference, right? Even if it's very close, even with sufficient people, I'm going to fall on it half one side, half the other, right? So sort of question is, why do we put so much investment in sort of rejecting the null hypotheses if the null hypothesis in theory is always false anyway? Okay. People kind of get sort of the argument here for sort of starting to question sort of the fundamental structure of sort of what we're doing here. Okay. Emil calls this cred factor. Everything's related to everything. If I get enough people and throw it in the mix, I don't know. Like I had a stat instructor in my graduate school that was very much into name letter effect. Anybody? This hypothesis that I have an implicit bias towards things that start with J or C. If I get enough data, I can start to see some sort of connections with things. I don't know. You might question whether or not that's an interesting or a useful thing to be excited about. I'm not trying to pass judgment on anybody's stuff, but again, it's just saying that if we go through and we get enough data and enough variables and run them through a giant enough correlation matrix, stuff's going to come up as related to other things, right? What we need to do is be very, very careful and thoughtful about what does this mean and what are the practical implications. Okay. Other criticism, null hypothesis isn't interesting. Okay. Again, our null hypothesis, our inference test is always like what it's doing is saying is something exactly zero, right? One, we can make an argument that the null hypothesis is always false because nothing is actually zero if we carry out enough precision. Other question is that like whether or not something is zero is not particularly interesting necessarily. Okay. Again, if I go through and I say I've got an experimental manipulation that results in 1/20th of a standard deviation increase or decrease, fine, but who cares, right? Like if it's not big enough to make any sort of practical impact on much of anything, right? I've got, for you clinical folks, I've got an intervention that produces change in self-reported symptoms that's not zero. All right, like so people are still miserable at the end of treatment. They're maybe have come down like a point or two, but that doesn't necessarily mean it's statistically different, but it doesn't necessarily mean that I've done anything useful with this, right? So I've got sort of multi-billion-dollar air quality initiative reduces pollutants by something that's a trivial amount and has no impact on anything, right? Again, sort of this conflation of statistical evidence of a statistical difference with something that's practical or meaningful, things along these lines, okay? So again, the argument sort of pointing out here that our null hypothesis testing doesn't explicitly address the precision or magnitude of effects, right? Just because I have evidence for a signal, it doesn't tell me sort of my formal hypothesis testing, my inference test doesn't tell me whether or not that has real world implications or the magnitude of what it is that I've sort of gone through and identified. And here's the thing, this Holbert quote, that I think it really kind of captures the problem with sort of our terminology in our language. You can make an argument, well, it's sort of semantics and things like that. Well, yeah, sure. But the words we use to describe what's happening mathematically in sort of our general terminologies or our general nomenclature, the word statistical word that use significant will never be understood by those without statistical training. I would say even with statistical training to mean anything less than its synonyms important and influential, right? I say I've found a significant difference, or I found a statistically significant difference. The data are significant. Anything I say there makes that sound important and meaningful, when in fact it's not. It just means that something's not zero, right? And so thinking about from a communication interpretation standpoint, recognizing that our tests don't give us any type of index of the importance or relevance of what we've done, or the practical meaning or the magnitude of an effect. They just say tell us whether or not something's different than zero, which is probably not going to be a terribly interesting factoid to know anyway. This is pulled from some stuff from Cumming and Fitch, which I think is very, very sort of in terms of thinking about problems with using dichotomous decision, statistical, non-statistical, is evidence for consistency in effects. Okay, so again, from a coming of pitch text, we've got a pair of studies evaluating efficacy of a new intervention for insomnia, based on a sample of 44. Lucky 2012 noticed a statistically significant advantage of the intervention relative to waitlist controls. By contrast, No Luck 2013 failed to observe a statistically significant effect in a similar sample of 36 patients. Okay. Now, if I was going to go through and take a look at that, what I would say is like, well, the data is unclear, right? Well, we've got one study that's found an effect, another study that's found an effect. So up in the air, not really clear on whether or not this is a useful intervention, right? Question that I should be asking myself is whether or not, sort of on closer inspection, whether we get consistent or inconsistent information and what information that we can draw from this, right? So if we're just going through on dichotomous decision, reject, fail to reject. On one, we have evidence for potential benefit of this intervention. The other one is saying it's inconclusive. We don't know if there's any benefit from this, right? Based on our inference tests. But if we go through and use this information to get something that's a little bit more useful, arguably, than yes, no decisions based on an inference test, and start generating confidence bounds for the difference around these two, now all of a sudden we start to see something that looks a little bit different, right? Daniela, based on sort of these confidence bounds, would you say that, so we've got luck and we've got no luck, have they found wildly discrepant findings based on this intervention? No, it's actually pretty consistent, right? We see that luck, a little bit bigger sample, they just fell sort of on this side of the null value of 0. No luck just kind of caught the other end of that thing, right? Now, based on our data, can we say, based on no luck's sample, that we have evidence for an effect of those data? I can't claim evidence for it, right? It could be anything from functionally no difference across these two to something that's sort of at least some difference. But as we start to sort of go through and stack these up, we see that these studies are really telling us kind of the same thing, right? One might have a little bit more precision. We're kind of jumping around. We might have questions about the extent to which the lower bound on these interventions are sort of consistent with something that's a practical and meaningful effect. But I would say that these two things are very consistent in terms of their evidence, right? And this is where our meta-analyses start to come into play, right? We never know anything. Like one study, any individual study tells us next to nothing about anything, right? It can start to hint towards something that might be helpful. But again, if this is my distribution of studies, I don't know if I'm right here close to the actual population value, if I'm way out here on the ends. There's no way to know. But as we start to generate a literature, as more people start to go through and run these studies and replications and sort of using slightly different methods and slightly different populations, what we can start to do is stack these intervals up around these effects and get a better sense for across the literature whether or not we have something that looks kind of like an effect, or if things are sort of jumping all over the place. So yeah, Haley found something in her study, but anybody else that's tried this is way down off of where Haley was at. Haley's was an outlier. Not saying that Haley was fooling around with data or whatever. Haley just might have had a situation where she had kind of an aberrant effect, but absent sort of understanding the rest of the literature, we have no way to know whether or not Haley's study was weird or different than anything else. If Haley's the only person who's ever published on this, who knows, right? So we're just left with a lot of uncertainty. But if we start going through, if we start looking at studies and just start making tallies on who found significance and who didn't, we're probably going to miss a lot of things. It's not a good way to go through and gauge consistency in literature. Okay. Yeah. So again, looking at our effect size, right? So we've got a mean difference here of 3.6, 2.2, pretty similar. Effect size, a little bit bigger effect size in this than that, but they're reasonably similar, right? I don't know that there's categorically different things going on in these two studies if I'm taking a close look at what's happening, okay? But what we do is we go through like, well, this study found something and it was significant. That study didn't find anything, it's not significant. Or that study didn't find, have sufficient evidence to reject the null, and so it never got published. And so now Olivia's study is nowhere in the literature because you just happen to catch the wrong side at 0 on that, when in fact it's a trivial thing. There's really no difference from whether you got it sort of on one side or the other, right? So getting like hyper focused on this dichotomous decision and sort of this significant language of significance really starts to set us back and leads us to make unfair conclusions. Also have bias against the null. Okay, we tend to associate our theoretical predictions with rejection of the null hypothesis, right? And so what happens in practice is that only those tests that are finding evidence for an effect or significance are the ones that are getting published. And so all the ones that don't find evidence for an effect aren't getting published, right? And so what ends up happening is that only those studies like Haley's, they're just kind of weird and finding stuff that's way, everybody out here, let's call this. Let's say there is a population effect, right? That population effect is D of 0.2. It's a small effect, right? Not sort of depending on what we're talking about, that might be important, it might not be important, but this is the population effect, right? And so when people are studying this, where are they going to fall? Mesa, just in terms of like when people are running and sort of running studies, if this is the population effect, where would we expect the effect sizes for most studies looking at this to fall in this distribution? Yeah, right. We're going to have stuff here and here and here and here and here, right? But then sometimes we're going to get folks like Haley who go through and catch something out here, right? So we got D equals 0.80, right? In actual fact, we got everything, most things kind of hovering around this, but if it's a small effect size and I have underpowered studies, am I likely to reject them longer? No, right? So do I publish these studies? No. Haley did, but she got a weird study, but this is the only one that's out in the literature. And so when Kate, you're going through and powering your study to look at this thing, what are you using as your metric for effect? Yeah. So you're like, sweet, I need to have 15 people. I'm golden. So you grab your 15 people, you run your study, where do you fall? Right around here. And again, so you fail to reject. And so now all of a sudden we've got a replication crisis. We got a replication crisis. We don't understand why no one can ever go through and replicate these studies. For certain, that's exactly what was going to happen if you understand how this process goes, right? Because if we only publish things that achieve statistical significance, we're only going to publish the random ass stuff that's way too high. And maybe this is extreme, maybe it's all up here, right? But these are all the ones that are going to get published. And what we've done is we've systematically created a literature that's inflated the effect size. And the rest of us are just chasing down this information that we have available. This is why in our meta-analyses, we hear about like sort of going through that gray literature, right? The dissertations, the unpublished studies, and things along those lines to try and get a better sense for what's going on with this stuff, right? So now when we go through and have that effect size plot, everything's kind of hanging out here. Haley hangs out here. Everything else comes down here. And again, it's not saying that you've run a bad study, you've been fooling around with weird stuff in your data. It's just that's going to happen sometimes. But if those are the only studies we're publishing, then we start to have problems, right? There's p hacking. That's a little bit different. This gets into some playing around with data stuff and things along those lines. Okay. And so because of this, we say probably effect sizes in our literature probably have substantial positive bias, right? They're overestimating the size of the population parameter. Alpha correction to correct for increase the threshold for statistical significance to correct for non-existent type 1 error, right? If the null hypothesis, if the whole null hypothesis is never true, can we ever have a type 1 error? No, because I can't say that something, I can't falsely claim evidence for an effect if there's always an effect, right? And so what I do, and Johnny, we had a conversation like, why not sort of just Bonferroni correct the hell out of stuff and make our criteria super high? Well, Problem is that we're probably going to do this. If I then go through and further increase the level to which I need to get to identify a significant effect, I'm just probably going to make this even worse. And so now all of the things that are super extreme are now going to go through and catch that threshold. Okay. And so again, those effects, luckily enough to meet increased threshold for a given study, further contribute to the overestimation of effect. Right. Now, this isn't to say that sort of correction for tests aren't important, can't be used effectively, right? But we need to be thinking about methodologically, does this make sense? When is it okay to use these? When should we be concerned about this stuff? Because that's certainly the case. If I got a sample of the size of like 30 and I run through 50 different pairwise comparisons in the sample, yeah, that's too much. We can't do that, right? But in terms of thinking about this replication crisis, some calls for, well, let's just like tighten up the criteria, right? Because we don't want people to be claiming evidence for an effect if there's not an effect. Well, the side effects of that might be that we actually make the situation worse as opposed to better, right? So some concerns about biases against the null, sort of having those studies be not even just not even picked up, but even reporting null effects, right? So I ran these other analyses. None of that stuff turned out. Important for me to report on that, so that's known then in the larger literature, as opposed to just cherry picking only the things that happen to turn out for me with these data. Yeah. This is what's, I mean, it's a big ship to try and steer. We've been trying to do it for like 60 years, but there are positive developments. I think things like Open Science Initiative, right, where your data is out there for everybody to look at and sort of go through and take a look. Pre-registration on stuff. If you've got a good idea and it's pre-registered and you sort of get to that says your methods are strong, this is a good test. Like regardless of what you find, it's going to be beneficial to the literature, because if you find an effect, cool. But if you don't find an effect, that's also important, right? So there are some mechanisms that are starting to help this a little bit. But on the other side, so we have to, like, it can't be a free for all. Like anybody who ever does anything, like sort of gets to publish it, like that's not helpful either, right? So it's a difficult balance with this. All right. Yeah, just another quote from Cohen about sort of like anything, if we misuse things and don't understand when we should be using things for what, if we just start sort of running ahead with, well, in this case, I do X, we're going to run into problems and perpetuate some of the difficulties that we've got going on in this in our field. Okay. Some confirmation bias stuff, right? Again, when we dichotomize into statistically significant or non-significant categories, this starts to become problematic because we don't weigh these equally, right? What ends up happening, we shouldn't do this, but what functionally happens is that those effects that fail to reach traditional thresholds for statistical significance, we interpret these as inconclusive, as we should, because that's what it means, right? What actually happens is people interpret these as there's no difference or no effect, right? But if we go through and we have evidence for an effect, what we tend to do is we accept these as conclusive, right? Because Daniela couldn't have found these effects if the null hypotheses were true. She did find those effects, and therefore, for sure, this has to be something going on in the literature or an actual effect, right? We don't say, well, maybe, looks like there's a signal, got to be careful. I get p equal 0.049, that's an effect, right? And we take that as gospel, right? Versus the null effects, we say, well, it's inconclusive, we can't say anything else, or we can't say much about it, right? So what ends up happening then is anything that goes through and sort of starts to become evidence for, I have evidence for an effect or a relation or something like that, we tend to take as gospel, right? And not thinking about like, well, the whole system's kind of screwy. There's a lot of reasons why someone might find an effect other than an effect is there. Oftentimes the way our system is set up, these effects are often probably have systematic inflation. If I go through and I find a single effect in a paper, who's done this or seen this? Like oh, well, Lindsay found this effect in a paper. And so then I go through and try and find a similar effect in my research and I fall flat on my face. Well, Lindsay found it, so it's real. My study must be messed up, or I didn't catch something or something along those lines. I don't know. Maybe your study is perfectly fine. It's possible that Lindsay's study is out of bounds. Just because you got it published doesn't mean that that's been sort of on a tablet handed down that sort of this is a real thing. There could be lots of things going on here, right? And so again, someone, and again, sort of you experimental folks have taken this a bit more serious, maybe a little bit too extreme in terms of stuff. I don't know that 50 studies for every sort of thing that paper you put out is necessarily helpful, but sort of like, oh, we had some people in the 60s find this effect and no one's been able to find that thing for the past 70 years. I mean, like, we would hope someone would catch on before we got to that point, right? But and again, sort of maybe sort of things were a lot different then, right? And so sort of realizing sort of that how the system is set up to almost ensure replication crises. No one should be shocked when this stuff happens. All right, this is what we do. Like, we find an effect, we're super excited, we're jazzed, big. I found this new thing, it's fantastic, right? Anytime we find an effect, we should be much more skeptical about this. We say, okay, sort of maybe, right? There could be something there. It's promising. And I'm not asking you to like crap on your own research or not sort of have sort of be excited when you find effects that you've hypothesized, particularly if you've got a good study, right? But for any individual study, so this is where we ought to be. Like, okay, looks like there might be something there. We've got a good signal. What are the strengths? What are the limitations? What are the next steps that would help me improve my confidence that sort of what I found is actually something that is sort of there and meaningful. Okay. But this is too excited about things. Yeah. Well, again, sort of I think the problem there, Mandy, is thinking about things in terms of significance, not significance. Okay. Sort of like anything else, like we are all trapped in these. We've talked about these, like we as human beings love binaries. Like, it's like, which one is it? Is it this one? Is it that one? The answer is almost somewhere sort of in between. And what we're going to do in this class is think more about sort of continuous evidence for, right? Sort of what's the strength of evidence for this effect, right? And again, if we meet the threshold set by our science, then by all means sort of say, like, we found evidence for this effect, but recognize the strength of evidence, right? Say, like, well, I found evidence for for a signal, but it's not super strong, right? Now, you don't have to say that. I mean, again, you don't have to fall on your own sword for everything that you ever do. But when we're evaluating other people's research and trying to say, what do we know about stuff? Thinking about things in terms of strength of evidence as opposed to effect and no effect is going to be a much more efficient way and a better way to go through and kind of think about things. All right. More criticisms. Fail to recognize our limitations. Okay. Again, I cannot stress sort of how important this is. All of our statistical methods work perfectly in a vacuum. Okay. Under certain assumptions, I can tell you the exact probability of obtaining data of certain characteristics, assuming the null hypothesis is true, right? But what are again, that's all of that our tests are doing. They're obtaining the results that we've seen, or more extreme than those observed in the current data, assuming that the null hypotheses and all auxiliary hypotheses are true, right? But all those auxiliary hypotheses, all the stuff that's just packaged in with statistical theory, is stuff that we never, ever, ever, ever achieve, right? Our sample is representative. Our sample is random. No violation of distributional assumptions. We generated our hypotheses before we collected the data, not after we got it and then decided what we were interested in, right? I've got a correct model. I've included all variables that are relevant. Those variables that aren't relevant aren't included. All my measures are valid. My measures are collected without error. These are the statistical assumptions, the mathematical, like theoretical assumptions of when this stuff works. Now we can relax these a little bit, but as soon as I start sort of dropping these 1 off, 2 off, 3 off, 4 off, what happens to the confidence in my interpretations? They start to fall apart, right? And now all of a sudden, sure, I might find evidence of an effect or fail to find evidence of an effect. There's lots of other things that can go into that outside of just my my study finding God the gospel truth of things. Okay, so things that our testing doesn't provide, probability that the null is true or false. That's the scientific question that we want to ask, but that's not the question that our models are asking, right? So we can't use null hypotheses to say the probability that the null hypothesis is false, the probability that the data were obtained by chance alone, because this is all non-chance stuff, right? Our null hypothesis, our p-value doesn't give us an estimate of the magnitude of an effect. We can calculate effect sizes and get into that, but that's not something that we get from our inference tests. The probability of replicating observed parameters, right? Again, and so this is from one of the readings, 70%, study of 70 academic psychologists, 60% thought that a p-value equal 0.1 indicated that the result would be replicated 99% of the time, right? I mean, we'll talk and you'll read a paper on the p-value does have some association with replication, but it's not a literal metric of replication, okay? So just misinterpreting our statistics. Null hypothesis testing doesn't give us direct support for whatever our theory is. Lots of reasons we might reject other than our theory is right, right? And so again, going back to Fisher in 37, right? Like sort of just like trying to say like, hey, and Fisher was one of the people who sort of developed these methods, right? Fisher is saying no isolated experiment, however significant itself, can suffice for an experimental demonstration of any natural phenomenon. One study alone doesn't demonstrate anything. We can sort of gives us evidence that sort of maybe there's something might be there, might be worth going through, improving on, and things along those lines. But no study individually tells us much of anything about anything. Okay, and sort of remembering that when we're going through and evaluating. So again, we get into sort of our statistical analyses and our models and our sort of software packages and things along those lines. It feels very much sort of like this. This is my R package, right? And this is sort of all the cool stuff that I can go through and take a look at. This is probably more consistent with what we're doing. We're kind of just poking around, trying to feel something out and say, do we have evidence of some signal somewhere in here, right? The fancy programs and things along those lines do a lot of cool stuff, and they make this a much, much easier process than it was 20, 30 years ago. But again, if we understand sort of the basics of what's going on, we need to be very careful in terms of the strength of our conclusions. Okay, so subset of minor issues, our entire sort of framework of understanding sort of what we think we know about things, right? Fundamental logic is flawed. The question we're answering isn't the question that we want to ask. My test hypothesis is always false. Rejecting the test hypothesis doesn't necessarily mean anything helpful. Our yes/no decisions are terrible. The agreed upon system that we use almost certainly creates bias. Our certainty about what we think we know far exceeds the accuracy of what we actually do know. And sort of as a consequence of all these things, we are either unaware of this stuff when we're going through and making our decisions, or willfully ignoring them because they're inconvenient and sort of not fun to think about. Because understandably, if I find an effect in my data, I'm pretty excited about that, right? And that's fine, so long as we're sort of taking that, making those interpretations, sort of understanding sort of the limitations of our knowledge and the types of things that we can infer. Okay. How are we feeling about this? It is a lot of problems. It is a lot of, I mean, it's kind of like how I feel sort of at the end of this. It's a lot of me like sort of standing up, shouting, waving my hands around how the system's broken, which there's nothing we could do about it necessarily. But I think important at this level for the types of things that you all are doing, to know, sort of understand our system, what it is, and what the limitations are there, so we don't fall in the same traps in terms of interpreting information, sort of running our own studies, things along these lines. Good, good. I'm going to hold you to that, and like the right. And this is the thing, like we can only work with the tools, and so this is the thing, like sort of like, why do we still do this, right? Like why, like with all these problems, like why are we still doing the same thing that we've known since the 20s and 30s, that this is problematic, right? Communication, like it's the nice thing is depending on what statistics we're using, there's always all sorts of different statistics and different distributions and things like that. One of the nice things about a p-value is there's a common metric, right? I know sort of, it doesn't matter if someone's doing a crazy ass SEM or a chi-square test, sort of I know what the p-value means. And so it's a nice way for me to go through and say, oh, if I'm interpreting it correctly, I can say, I have sort of this study is, I guess, looking, it seems like it has evidence for whatever effect they're looking or not, right? It's a nice shorthand way of communicating strength of evidence. And so that's arguably a very good thing. It provides us with an agreed upon standard for dichotomous decisions, right? It's easy. If we just say, and this is the thing, like I'm not, oh, oops. Anybody confused on whether or not that's more or less than 0.05? That. Okay, cool. So we don't have spend a whole lot of time in class determining whether or not you know whether a number is bigger or smaller than another number to determine whether or not something's significant or not, right? So like you telling me that a p-value is less than 0.05 by telling me that it's significant is not terribly useful for me, because that just tells me that you understand numbers and what's bigger or smaller than something else, right? And so what I'm going to challenge you all to do, and so what we're going to do in this class, is try and not use that language. Now, this isn't to say that if you're in your labs and in your papers and in your sort of milestones and stuff like that, that if I'm on your committee or sort of looking at your stuff, then I'm going to judge you harshly. No, all of this stuff, you should do whatever your advisor is telling you to do that thing. Don't ever say Josh said not to do this, because that Josh said not to do this isn't a reasonable rationale for anything, right? They're going to be the ones that are guiding you through your areas and things like that. But what I want you to be doing in the back of your head is thinking about, okay, I know what this means, and I can sort of frame this and think about this in a way that's responsible and keeps me from falling into some traps. Okay. So another reason, sort of we teach what we learn. Sort of we always just learn P that's sort of significant, not significant. And so that just kind of gets passed along, right? And sort of perpetuates things. Lack of consensus on a better alternative, right? Like, so I can complain about things all day, but if I don't have a solution to something better, fine, I guess, right? And we really don't, right? I mean, we have some different procedures and things like that that add into some things, but just practical limitations, we don't have something that's necessarily clearly better, right? And so we're kind of stuck with what we've got to some extent. And then we've assigned it professional value, right? In our field, sort of we put a premium on these p-values, and low p-values are sort of better than high p-values. And so because of that, sort of this grants me access to publications and grant money and things along those lines, right? And so we've incentivized this. And if all of a sudden I told you, hey, all the dollars in your bank don't mean what you think they mean and they're not any good, that would be a difficult thing for you to go through. Olivia doesn't like that at all, right? This is kind of what we've built our entire science around, and so it's hard, change is slow, right? So some things that we do agree on, right? We've got a lot of different statistical techniques that can help us sort of look at different things, but we have to use these sensibly and informed by our good judgment, right? So we can't just like plug things into a computer, identify a p-value, and then just start claiming victory or failure based on that, right? How talking about declaring something to be statistically significant is no longer significant, is no longer sufficient. We need to tell something about the difference itself, confidence limits, things along those lines, the power of our test. We're getting better at this, okay? Within the context of the null hypothesis test, sensible conclusions are based on intuitive weighing of factors such as p-values, power, effect sizes, number of observations, finding from related work, substantive theory, performance of other models, right? What we're trying to do with our research is pull things in together to have converging evidence for, you know, it's not just this p-value that I got that sort of suggests that things are looking good. I've got, this is aligned with previous research and it's consistent with theory. I've got a reasonable effect size. I had a reasonably powered study for this. And all of these things are coming together to kind of make me feel pretty confident that what I've got is maybe sort of looking promising in terms of the types of things that we're looking at, okay? Strong consensus within methodology. One of the precision of estimates, right? These are getting at our confidence bounds, our magnitude of estimates. These are effect sizes and the extent to which our lower bounds and upper bounds are sort of different from some practical cut point. Placing context research results in the context of prior research and existing knowledge. Know your literature, right? Know studies and be able to pull to see, like, Johnny's got this thing and be like, okay, this other study was looking at the same thing. Is my stuff in line with that? If it is, cool. If it's not, I should be thinking about why it's not. Like, what was different there? What can I learn about this? The phenomena of interest, sort of based on how it plays into other studies. Evaluating our methodology, right? I've said it before, you can't divorce statistics from methodology. If you got garbage methods, you got garbage measures, we're not going to be able to tell anything about anything, right? I cannot statistically fix poor methodology. There's no correction factor for this, okay? And then recognize the limitations of our framework, right? Recognizing that our effects are a best case scenario, okay? Like in a vacuum, like if I had a perfect situation, this barely tips over the threshold for the benchmark for interpretation. So maybe I should have pumped the brakes a little bit before I make strong sweeping conclusions about sort of what I've found here, okay? And again, just recognizing that it's not just sort of just because I pulled down a pull down menu from SPSS and gotten a p-value doesn't mean that that p-value means anything or that anything that I've done contributes to anything, sort of absent sort of some additional sort of information and thinking about sort of what it is I'm doing, what are the limitations of these data, what can I think and infer from this stuff. So things that we can do, all right? Report exact p-values. Reading some of the stuff in the assignments that you're reading, sort of thinking about p-values as a continuous measure of compatibility with the null hypothesis in the data. Bounded by 0, completely incompatible, the data are impossible under the null hypothesis given it. Like, if the null hypothesis is true, these data functionally cannot have occurred, right? Would be a p-value of 0 or 1, no incompatibility from the test, right? Now, again, that's all sort of going into all those ancillary sort of hypotheses or assumptions, but basically thinking about your p-value as a continuous measure of compatibility of the data with the null, right? It's not giving you a specific percentage or likelihood of replication or things along those lines, but again, p equals 0.043 and p equals 0.000000824. Those are very different results in terms of strength of evidence, right? And sort of recognizing that the two things are different, right? And sort of thinking about that p-value not as evidence, or sort of it tells me whether or not I have an effect or not, which is that dichotomous thinking. This is giving me evidence to suggest that sort of, yeah, sort of this, the extent to which the null hypothesis is sort of reasonable, compatible with the data. Okay. Replace threshold of significance. People have suggested that we replace the threshold of statistical significance for novel discovery to p.005. Anything from 0.05 to 0.005 is suggestive. It's a suggestion that's been made. The problem is if we start sort of cranking out the goalposts, the problem of potentially making sort of that bias that we talked about even worse. So some criticisms against this piece of things. Augment statistical tests or augment interval estimates and statistical tests with S values. We're going to talk about these. These little asterisk ones are ones that we're going to work on in class. So this is taking that p-value and transitioning it into a slightly different statistic that maybe has more intuitive meaning than that p-value. Thinking about sort of the evidence is consistent with the likelihood of consecutive heads on a fair coin, right? So if I tell you, Mandy, that I have a fair coin, and I throw heads, and then I throw heads again, and I throw heads again, and I throw heads again. How many heads do I have to get before you start to decide that maybe I don't have a fair coin on my hands? Yeah, I don't know, right? With each consecutive head call, like it starts to get less and less likely that I have a fair coin. Thinking about our p-values kind of in that way, and we'll talk about that a little bit more. Okay. Augment interval estimates and statistical tests with database odds. Okay, we're going to talk about this Bayes factor bound, right? Thinking about this as the odds ratio specifying the strongest case for the alternative hypothesis relative to the null. Okay, saying instead of actually using this to ask the question that we actually want to know, sort of what's the likelihood of the null hypothesis relative to the alternative, and sort of using the evidence that we do have to create an upper bound for that, okay, which is an interesting idea. Some analyses based on minimum practically significance tests. This is sort of thinking about specifying a thick null, right? So the idea here being that instead of saying something is exactly zero, this starts to get into more like physics types of sort of approach back. Well, I'm saying thing that falls within not just zero, within this bounds would be inconsistent with evidence for my hypotheses, right? Because again, then we sort of start to get away from, oh, hey, this isn't exactly zero, therefore it's meaningful. Back, nope. We're saying that anything within this bounds would be inconsistent with sort of what we're trying to find, right? As opposed to just choosing a specific point estimate of zero, okay? Some second generation p-values. This was an idea that sort of is incorporating an interval null, kind of caught on for a while in experimental stuff, but then people didn't like there's some problems with this, so you don't see it. You'll still see people talk about it, but it wasn't something that actually sort of turned out. Oh, whoops. And then sort of different sort of things that sort of bring in existing knowledge from other literatures and start to go through and type of thing. So this is all from these are all sort of solutions and suggestions from some of the readings that I've had you go through and read. Some of these things start to be a little bit more practical for sort of strengthening inference. What we're going to do is report exact p-values, right? And again, your advisors will probably tell you not to do this, and that's fine. Don't do it if they're telling you not to do it. But for this class, I want you to do just kind of sort of lock in this idea that this p-value does have is a measure of the extent to which my data are incompatible with the null. And if it's very, 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 very small, that means that my data are very, 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 very incompatible with the null. Versus if they're just right there on that 0.049, they're incompatible, but not as incompatible as sort of something that could go out there, right? So we'll talk about reporting p-values exactly. We'll talk about working in S values and Bayes factor bounds and things like that, and just using that to think about things not in terms of yes, no decisions, not just significant, not significant. Think about things more in terms of strength of evidence for sort of the effects that we're looking to find. Okay. All right, and that's it. We didn't get into t-tests today, but that's fine. We're sort of right dead on track with where we were supposed to be. Any questions? So it sort of brought you into a philosophy class here, right? Go through, take a look at this this material, sort of make sure that you have a general understanding of sort of the strengths, limitations, some of the concerns, both conceptually, practically, with our method of trying to understand things, or sort of how do we How do we know the things that we know? So want to make sure that you're sort of strong on this, because it'll help as we start to sort of go into our actual sort of tests and analyses. Again, we did a lot of dumping on null hypothesis significance testing. And then for the rest of the year, we're just going to do null hypothesis significance testing. But I don't know. I'm fine sort of being open about the limitations of my tool if it's the only tool I got in my belt. So unless we sort of go straight over into like straight Bayesian stuff for the whole rest of the year, then that's not going to serve you well, because that's not a language that most of our science sort of recognizes or sort of plays with. So we'll use the tool. We'll just know what the limitations of the tool are and sort of make sort of better inferences because we understand where the landmines are. That sound good? Awesome. Thank you all so much. You're terrific. We'll have problem set 3 will be due next Friday, not this coming Friday, but the following Friday at noon. So make sure that you're planning appropriately for that. If you haven't gotten into that yet, make sure that you do, just so that you don't sort of run into a rush with your group, so that you have enough time to sort of go through and catch up with me or Matt if you have questions about any of those problems on there. All right. Awesome. Thanks, everyone.